Very pleasant morning to all. I hope that you all stay safe and healthy. I am Saravana Kumar, Assistant Professor in the Department of Mechanical Engineering. It is a great pleasure to share a few words about our college and our department. Francis Xavier Engineering College is located at Tirunelveli City and it was established in the year 2000. FX Engineering College comes under SCAT group of institutions. We offer 6 UG programs, 10 PG programs, and have scholars carrying out doctoral studies in our research centers. Our college has achieved many awards. Among all, I would like to list a few to your knowledge. We have got gold category for Industry Linked Technical Institute, which was awarded by AICTE CII survey for 2 consecutive years. In Chronicle Engineering College survey, we achieved third position among 19 engineering colleges in India. In Times Best Engineering College survey, our college has obtained 15th rank in Tamil Nadu and 108th rank in India. The Department of Mechanical Engineering is the largest department on campus with 600 plus students, 35 faculty members, and with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industrial Safety Engineering. The UG program is accredited by NBA, the National Board of Accreditation. Our department is permanently affiliated to Anna University. Apart from course-defined curriculum, we offer a number of value-added courses and impart various skill training to the students. In addition to well-equipped laboratories that comes under curriculum, we have a few special labs for encouraging innovation and new product development. We also have a strong academy for training students to appear for GATE exams. Our department has signed many MOU with leading manufacturing and service industries. We also offer international certification program on Fanuc CNC programming, computer-aided design, non-destructive testing, and BMW Hyundai Industry Associated Laboratories. Our students are actively participating in many technical competitions, winning prizes and bring glory to our department. The research area of our faculty members are bioenergy combustion, solar desalination, green manufacturing, waste heat recovery, biomass gasification, and composite materials. We have also organized many international conferences, workshops, and funded seminars. I hope this session will be more useful for all of us. With this introduction, I welcome all the participants for this session. Hope we will have a great learning today. Thank you.
Hello everyone, a very fine morning to all. I am so glad in introducing our honorable speaker, Dr. Vikas R. Kalkar. He is one of the distinguished professor in the field of mechanical vibrations. He is presently working as an associate professor in the Department of Mechanical Engineering at Garda Institute of Technology, Maharashtra. He completed his PhD degree in 2018 from Satyabama University, Chennai. Aside from his talents and backings, Dr. Vikas is prestigious author for number of papers on the subject of mechanical vibrations. He has published 13 papers in international journals and also presented his work in many international conferences held at different prestigious institutes like NIT and PMME elsewhere conferences. On a final note, he is also a fascinating individual and we are very pleased to have such an eminent professor with us today to discuss about the effect of cracks on vibration parameters of a cantilever beam. With this introduction, I welcome Dr. Vikas Kalkar sir for this event and I hand over the session to him. Over to you, sir.
Today, I am giving webinar on investigation of the effect of cracks on vibration parameters of a cantilever beam. Actually, cantilever beam has many applications. Like it is used in turbine blades. Means in the turbines, blades number of blades are there, and all the blades are possessing cantilever boundary conditions. Then wings of aeroplane. Then tall building means suppose one building is there and suppose wind force is acting, means at that point of time that particular building is acting as a cantilever type of structures. Then another application is there, cantilever type of bridges. Means cantilever beam is having number of applications. Suppose uh, take two examples. Suppose in the first case, cantilever beam is not carrying cracks, right? And suppose we are giving excitation, or suppose we are giving disturbance to the cantilever beam, then its dynamic response will be as per our expectation. And consider another case. Suppose cantilever beam is carrying some defects like cracks, some slots, or something like that. And suppose this disturbance is given to the cantilever beam, then what will happen? Its dynamic response is going to change. Now our requirement is that cantilever beam should not carrying any kind of defects, because suppose it is not carrying, suppose it is carrying defects, then what will happen? That magnitude of that particular defect is going to increase in the structure with respect to time in the service. Suppose we put suppose we have one cantilever beam, suppose we put that cantilever beam in the service, and suppose it is carrying defects, then what will happen? Defects like cracks or something like that, then what will happen? The magnitude of that particular defects will be getting increase in the structure, and at the end that particular structures or cantilever beam will give catastrophic failure. That we don't expect. Because of that, it is very essential to do the study of crack cantilever beam in the regard of health monitoring of the cantilever beam. Suppose, and for that particular purpose, suppose our expectation is that structure should not fail. Because of that, we should do something. Means we should do the structural health monitoring of the cantilever beam. Means suppose cantilever beam is carrying crack, then in the earlier stages only we should locate, or we should identify the presence of cracks in the cantilever beam, so that we can avoid the catastrophic failure or failure of the cantilever beam. Because of that, this study is very important. Actually, vibration based crack detection is divided into two types. Means one 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 case is corresponding to forward problem, and another one is inverse problem. Now I will do some introduction in the regard of forward problem. In the forward problem, what we have to do? Artificially, we have to take the cracks on the cantilever beam, and we have to disturb that cantilever beam using impact hammer or vibration exciter or something like that. And we have to check how dynamic response of the cantilever beam is going to change. Dynamic response means what? Natural frequency, then resonant amplitude, stiffness, mode shapes, and all that. Means in the forward problem, what we have to do? We have to study. Means we have to see how the response of the cantilever beam or cantilever type of structure is changing due to the presence of defects. And in the inverse problem, what we have to do? We have to identify the location of the crack or depth of the crack in the beam. Means in the inverse problem, what we have to do? We have to use the inputs of the forward problem. In the forward problem, we have the value of natural frequencies like first, second, third natural frequencies, then mode shapes, mode shape number 1, mode shape number 2, mode shape number 3. Means in the inverse problem, we have to use we have to use either mode shapes or stiffnesses or natural frequency as an input for predicting the possible crack detection in the beam. Means that is inverse problem. And when we will looking into different cases, at that time most of the things will be getting clearer. And there are different reasons due to which defect is producing the cantilever beam. Like suppose we have one cantilever beam, and suppose it is carrying localized corrosion, localized erosion, and suppose the endurance strength of the cantilever beam, suppose it is not up to the mark, then what will happen? And when suppose we put that particular cantilever beam in the applications, then what will happen? At the starting we will get minute crack, and because of action of fatigue loads or cyclic loads, what will happen? That means magnitude of the crack is going to increase, and it will finally leads to failure. Means defects are the main cause of producing the cracks in the beams. Means we expect that our cantilever beam should not carry any kind of defects, so there is no problem of cracks and all. Now we will be looking into the first case. And the title of the first case is study of free undamped and damped vibrations of a crack cantilever beam. Now I will with the help of diagram, it is better to explain. I will explain with the help of diagram. And just see, in this particular study I have considered 21 crack cases. Let me see, 21 only. And I had taken on some specimens, I had taken transverse crack, and on some specimens I had taken oblique cracks, means 10-degree oblique crack, 20-degree oblique cracks, and all that. Means I had studied how the dynamic response of the cantilever beam is going to change because of presence of transverse crack, because of presence of oblique crack. Now question is that why I had considered transverse crack and oblique crack. Suppose our structure is carrying some localized defect right now, then it is not necessary that defect should be like this. Sometimes defect will be like this. Your localized corrosion will be like this. Sometimes localized the orientation of the localized corrosion will be like this. Sometimes it will be like this. And suppose means suppose our cantilever beam is carrying the crack, carrying oblique crack, then we must know what is the effect of oblique cracks on the cantilever beam. Right now, suppose our cantilever beam is carrying transverse crack, then we must know what is the effect of transverse crack on the dynamic response of the beam. Means definitely cracks will be either transverse type or oblique type, and we should know how the dynamic response is changing for this kind of crack or other kind of crack. And because of that, from study point of view, I had considered three types of cracks, means two types of cracks, transverse and oblique. Right now, sir, this is our cantilever beam, and here cantilever boundary condition has applied like this. And this is the free end of the cantilever beam, and this is transverse crack. And in the top view, you can see transverse crack is present along the width of the beam, means along this direction. And this is the top view of the another case of cantilever beam, and in the top view you can see the oblique crack. Just see, this is x, this is y, and for this diagram this is x and this is z. Means this direction, z direction, is along the width, and because of that you can see the oblique crack. Right now, sir? And for that I had done some experimental study. Means I will show you over here. This is my experimental setup, and this is picture. Means the purpose of this particular picture is to hold the specimens. Means this is our beam, and this beam is supported at the ends, and means we have applied cantilever boundary condition on this particular beam with the help of pictures. And this is accelerometer, and this accelerometer is connected to the FFT analyzer. Okay, and this is impact hammer, this one. And suppose we have to vibrate this particular beam, then what we have to do? We have to take this impact hammer and we have to apply the blow on the cantilever beam in this plane, in the vertical plane, so that what will happen, bending mode of the cantilever beam is purposely disturbed, is purposely disturbed or excited. Means suppose we have given the blow with the help of hammer on the cantilever beam over here, then what will happen? It will vibrate, okay, in the vertical plane. Means like this, right now. And finally, we will get the value of dynamic response, like natural frequencies and damping factor and all that. Okay, this is all about the experimental setup, right now, sir? Now this is finite element modeling and analysis. Means in the experimental analysis, through the experimental analysis, I had got the value of natural frequencies and damping factor. And for validating the results, what I did, I had used ANSYS software, and I had created a model like this in ANSYS software. Means I had used these geometric properties. Means I will show you geometric properties. These geometric properties I had taken. Means cross section point 20 mm by 20 mm length. I had taken 360 mm, and these are the metal properties I had used. Means in earlier days I had tested all this property in Elka lab Pune, and in the finite element analysis, what I did, first of all, I created a model of these geometric properties, and afterwards I created required cracks at the required locations, and afterwards mesh I had meshed the finite element model using solid 186 element. I had used solid 186 elements because this is 3D model. So, and due to that, I had preferred solid 186 element for matching this particular model. And I had applied boundary condition over here that you can see. This is mesh finite element model. And afterwards, I had carried out the analysis, modal analysis, as well as harmonic analysis for getting the value of natural frequencies and resonant amplitude. This is about crack zone details. And this is one experimental plot. Means number of cases I had considered. Means on some specimens I had considered transverse crack. On some specimens I had considered oblique cracks, and means number of cases I had considered, and here I have shown the natural frequency plot of one particular crack case, and for that particular crack case, using this is experimental plot actually. I had got the value of natural frequency equal to 99.12. This one. Here I means this peak is giving the value of natural frequency. Now, and using this particular graph, I had calculated the value of natural frequencies. Damping factor. Means and this is suppose for calculating the value of damping factor, I had used this curve. Means one formula is there, 2 zeta is equal to f. Means what I did in the, this is one graph, and I had plot one horizontal line at a distance of 0.707 times of this peak amplitude. Means I had got a line over somewhere over here, and this was f2, this was f1, and using bandwidth method, I had calculated the value of damping loss factor. Means 2 zeta is equal to f2 minus f1 upon natural frequency, and natural frequency means this value. Peak means this highest point we have to project on the x-axis, and that point means that line will intersect on the x-axis over here, and this point will be giving us the value of natural frequency. It means this is natural frequency, and f2 will be this value, f1 will be this value. And this line, what is the distance of this horizontal line? It is 0.707 times of this distance, peak amplitude. Now I will expand number of graphs. Means first graph between variation of natural frequency ratio versus crack depth ratio. Now first of all, we must know what is natural frequency ratio. Actually, what is natural frequency ratio? It is the ratio between natural frequency of cracked beam to the natural frequency of uncracked beam. It is called as natural frequency ratio. Right now, sir? Means value of natural frequency of uncracked beam is always greater than natural frequency of cracked beam. Right now, means suppose we are considering crack beam, then definitely value of this ratio is less than 1. Is definitely less than 1. Because value of natural frequency of crack beam is always less than 1 only. And this is the x-axis indicates crack depth ratio. Crack depth ratio. Now what is this crack depth ratio? Means now from the diagram I will show you crack depth ratio. I am talking about crack depth ratio. Just see, the A indicates crack depth and H indicates depth of the cantilever beam. Then what is crack depth ratio? It is the ratio between depth of the crack and depth of the beam. It is called as crack depth ratio. I think that you all understood. Okay. Now just see from all the graphs, means experimental 0 degree, FEM 0 degree, means 6 cases, means 3 cases were there, and 6 cases are were there, means 3 for experimental and 3 for handheld element. Now here we will looking into the graph of natural frequency ratio versus crack depth ratio, and our graph is like this. Our graph is like this. Our graph is like this. Now what it indicates? What? 1 minute. What it indicates? Suppose we are increasing the depth of the crack in the beam. At that point of time, what will happen? The value of natural frequency or natural frequency ratio is going to increase. Here I had used R symbol for indicating the natural frequency ratio. Now once again I will explain. Suppose we are increasing the depth of crack in the beam, then what will happen? The value of natural frequency goes on decreasing. Now what is the reason? That I will tell you. Suppose we are considering small crack depth, then suppose we are considering this particular point, means we are considering small crack depth. Right now, because value of crack depth, suppose value of crack depth ratio is less, means we are considering small crack depth. And for small crack depth, what is the value of natural frequency ratio or natural frequency? It is large. Suppose we are considering this particular point. For this particular point, value of crack depth ratio is more. Then we are getting less value of natural frequency. And for this particular point, value of natural frequency is least. Now, what is the reason? Suppose we are considering this particular point. Okay, and for this particular point, value of natural frequency is more, because at this particular point we had removed less amount of material from the crack cantilever beam, and because of that, what will happen? The stiffness of the cantilever beam is definitely reduced, but it is not going to reduce significantly. Means small reduction in the stiffness is there, but it is not abrupt, and because of that value of bending moment at the crack will be less, and due to that the value of natural frequency is more. Once again I will repeat, because of for getting small crack depth, we have removed less amount of material from the cantilever beam, and because of that the value of stiffness of the cantilever beam has reduced, means through small value, and due to that the value of natural frequency is decreasing, but it is not decreasing significantly, and because of that we have got large value of natural frequency at this particular point. And just see this particular point. At this particular point, okay, this particular point indicates largest value of crack depth. Largest value of crack depth means we have removed largest amount of material from the cantilever beam. and because of that there is abrupt or significant reduction in the stiffness of the cantilever beam. And in vibration mode formula is there, natural frequency is equal to under root of k by m. Right now, suppose abrupt reduction in stiffness means abrupt reduction in natural frequency, and because of that we are getting least value of natural frequency or natural frequency ratio. Means this is all about the interpretation. Means when we will increase the depth of the crack in the cantilever beam, at that time the value of natural frequency is going to reduce in the cantilever beam, and then that is going to happen because of all these reasons. Now we will make focus on transverse crack, means 0 degree crack, 10 degree crack, and 20 degree crack. Now just see, for 20 degree crack the value of natural frequency is largest. For 20 degree crack, suppose all these points are corresponding to, this point is corresponding to 0 degree crack, this particular point is corresponding to 20 degree crack, and this particular point is corresponding to 10 degree crack. Right now just compare all these points. For 20 degree crack we have got largest value of natural frequency, and for this point we have got comparatively less value of natural frequency for 0 degree crack. That I will show you over here. For 20 degree crack maximum, for 10 degree crack intermediate, and for transverse crack or 0 degree crack comparatively less. Now I will tell you from this diagram. This is transverse crack. Because of transverse crack, largest value of bending moment is producing at the crack, and suppose we are considering that oblique crack in the cantilever beam. Okay, means at the same location we have to take, at the same location we have to take one crack. Okay, and we have to maintain the same crack depth. Suppose we are considering two cases, a case of transverse crack and case of oblique crack. Then location and crack depth we are not supposed to vary. We have to maintain the same location for this crack, and for this crack we have to maintain the same crack depth for this crack and for this crack case. Just we have to change the orientation of the crack. Means this is transverse crack, means your crack will be like this in the top view, and in the oblique crack it is like this. And because of presence of transverse crack, largest value of bending moment, okay, is producing at the crack, and because of that the effect of damping is remaining comparatively more for this particular case. And just see this oblique crack. In this oblique crack is going towards the free end. This is the free end. Okay, and this oblique crack is going towards the free end, means like this. And because of that when we will compare the value of bending moment for this crack and for this at this crack and at this crack, then value of bending moment is comparatively less for this case. Suppose the value of bending moment is comparatively less for this particular case, means value of damping is comparatively less for this particular case. Suppose the value of damping is comparatively less for this particular case, means less resistance to vibrations, and because of that for this case we are getting comparatively larger value of natural frequency. That I will show you over here for 20 degree crack. Because just see, for 20 degree crack we are getting larger value of natural frequency, because whatever damping effect we will get at the crack, it is comparatively less for the case of with respect to case of transverse crack. Because of that we have got largest value of natural frequency over here. This is all about the interpretation, and this is the this graph is giving the relationship between variation of natural frequency with respect to crack depth ratio for 0 degree crack, means for 0 degree crack, this is for 10 degree crack, and this is for 20 degree crack. And all these graphs are included in this case. Means this is the detailed views, detailed graphs. Now next point is what variation of natural frequency ratio versus crack location ratio. Now natural frequency ratio you already know. Now I will make my focus on crack location ratio. What is crack location ratio? That I will tell you. so that you will understand. And it is means indicated using this symbol L1 by L1, L1 by L, L1 of an L. What is crack location ratio? It is the ratio between L1 and L that I will tell you. I will show you over here. Once again, we should. I should show you this diagram. Just see, sir. And what is crack location ratio? It is the ratio between L1 and L. Now, what is L1? That I will show you. L1 is what? The distance between the crack and the cantilever end. What is L1 distance? It is the distance between the crack and the cantilever end. It is called as L1 distance. Means when the value of crack location ratio will be 0.5, then we will consider the crack at the midpoint. Suppose we are considering the crack at the midpoint, then value of crack location ratio will be 0.5, like this. Okay, now see this graph. Now I will tell you, means we have to study the relationship between natural frequency ratio and crack location ratio. Now what we have to do, we have to take 4 specimens, and on the 4 specimens we have to maintain the same crack depth. Means crack depth we are not supposed to change. Means we have to take unique crack depth, just location we have to change. Means on one specimen, on first specimen, we will provide the crack on the cantilever beam at a distance of 60 mm from the cantilever end. On the second specimen, 120 mm from the cantilever end. On the third, 180 mm location from the cantilever end. And on the last, 240 mm from the cantilever end. Right now, means suppose we have 4 crack specimens, then using A50 analyzer, we have to test all the specimens one by one. Suppose we had tested specimen number 1, then for specimen number 1 we had got this value of natural frequency or natural frequency ratio. Suppose we had tested second specimen, cracked specimens, then value of natural frequency will be like this. Natural frequency ratio, natural frequency will be like this. For the third, it will be like this. For the fourth, it will be like this. Means what it indicates? Means what we have to do on all the specimens, we have to take unique crack depth like 4 mm or 8 mm, and we have to change the locations. We have to keep on changing the location of the crack. Then what will happen? The value of natural frequency is going to increase. The value of natural frequency is going to increase. Now I will tell you the reasons. Once again, I will repeat. When we will increase the distance of the crack from the cantilevered end, then value of natural frequency is going to increase. Once again, I will repeat. Then we will increase the distance of the crack from the cantilevered end, then value of natural frequency ratio or natural frequency is going to increase. From the straight line you can see. Now for this, some interpretations are there that I will means that we will see with the help of this diagram. Okay, suppose suppose we are providing the crack at these particular locations. Means suppose this is the location of the first crack. Means this crack is nearer to the cantilevered end, and definitely this particular crack is going to produce largest value of bending moment or largest value of damping effect in the cantilever beam. And suppose this particular case is producing largest value of damping effect in the cantilever beam, then definitely value of natural frequency will be less. Just see. Means for the first case, the value of natural frequency is less. Then in the second case, what we have to do? We have to increase the distance of the crack. We have to increase the distance of the crack. Means in the first case, we had considered crack over here. In the second case, we have to consider crack over here. Means we had increased the distance of the crack from the cantilever end. And when we will test such specimens, at that time we will find that the value of damping effect at this crack is comparatively less. Suppose the effect of damping is comparatively less, means less resistance to vibration, and because of that, value of natural frequency is going to increase. And because of that, for the second point, value of natural frequency is comparatively more. That I will show you again. For the second point, the value of natural frequency is comparatively larger. For the third case, what do we have to do? Again, we have to increase the distance of the crack from the cantilever end, and we have to test the specimen. Then, at the crack, value of bending moment or damping effect will be comparatively less. Again, means compared to this location and this location, whatever value of damping effect we will get at this point, or at this case and this case, and because of that, what will happen? There will be less resistance to vibration of the cantilever beam, and because of that, the value of natural frequency is going to enhance or improve, and because of that, we are getting comparatively larger value of natural frequency over here. And for the last case, means what this particular point indicates, means our means we have provided the crack on the cantilever beam nearer to the pre-end. Means in the last case, we have to provide the crack, okay, over here, or over here. Means in the case number 4, we have provided the crack on the cantilever beam nearer to the pre-end. And in this case, what will happen? Even though, because of this crack, what will happen? We will get least value of bending moment at the crack. Means suppose at this location, even though crack is present, but when we will see the value of bending moment at the crack, or when we will see the effect of damping at the crack, it will be very less. Means least resistance to the vibratory motion, least resistance to the vibratory motion, and because of that, we will find that the natural frequency of uncracked beam is equal to the natural frequency of this particular crack case, and due to that, we are getting largest value of natural frequency for the last location. For the last location, and these are the reasons due to which the value of natural frequency increases as we increases the location or distance of the crack from the cantilever. And these are the means detailed diagrams for transverse crack, 10-degree crack, and 20-degree crack. Again, we have to look into another graph, variation of damping loss factor versus crack depth ratio. Now just see this particular graph, and you are getting straight line over here. What it indicates, suppose we are increasing the crack depth in the beam, then value of damping factor is going to increase. Now it is very easy. Suppose we are keep on increasing the depth of the crack in the cantilever beam, then we will be getting lesser and lesser value of stiffness, and because of that, the value of damping effect will be significant. Means for this particular case, the value of damping effect is least. For this particular case, the value of damping effect is comparatively more. For this case, again comparatively more, and for this particular case, the value of damping effect is maximum. Suppose the value of damping effect is maximum, means value of damping factor is maximum. Suppose effect of damping is minimum, means value of damping factor is minimum. Due to this particular region, the value of as we increases the depth of the crack in the cantilever beam, the value of damping factor is going to increase. And I have plot this particular graph for different cases, means for transverse crack as well as for the oblique cracks. These are the separate cases. All these cases we have considered in this diagram only. Just these diagrams show the difference between the experimental and equivalent results. Again, this graph we have to study variation of damping loss factor versus crack location ratio. Now again, it is very simple. I already explained you. Suppose the crack is present at the free end of the cantilever beam, then effect of damping will be minimum. And suppose effect of damping is minimum, means value of damping factor is minimum, and just project this point on the y-axis. You are getting this value of damping factor. because this location, because this crack is present in the cantilever beam, means this crack is present in the cantilever beam nearer, means this crack is nearer to the free end of the cantilever beam, and due to that, effect of damping in the crack beam is less, and due to this particular reason we are getting this value of damping factor. Now suppose we are considering this particular point right now, means we are considering the crack location which is which is which is nearer to the cantilever end, which is nearer to the cantilever end, means what will happen, the value of damping factor or effect of damping factor is remaining significant for this particular case. Suppose the effect of damping factor is remaining significant for this particular case, means value of damping factor will be maximum. Just see, means what is the, then how we will do the interpretation, when we will increase the distance of the crack from the cantilevered end by keeping the crack depth constant, then value of damping factor is going to decrease because of this particular reason, now you can see for 0-degree crack now the value of damping factor is maximum, and for 20-degree crack now the value of damping factor is minimum. Means we are considering the same location, just consider, means for this point, all these points location is same, crack depth is same, but we are getting different value of damping factor for 0-degree crack, 10-degree crack and 20-degree crack. For 20-degree crack, for 0-degree crack we are getting maximum value of damping factor, means transverse crack, because of transverse crack largest value of bending moment or largest effect of damping is going to produce in the cantilever beam, and because of that here we are getting largest value of damping factor. And for 20-degree crack it is minimum. Just see, suppose this is 20-degree crack, FEM 20-degree crack or experimental 20-degree crack, and just see the value of damping factor, it is comparatively less. And for 10-degree crack, for 20-degree crack minimum, for transverse crack maximum, and for 10-degree crack, it is in between 20-degree and transverse crack. Means what is the means we will say that suppose we are increasing the crack angle, means 0-degree, 10-degree and 20-degree. Means suppose we are increasing the crack angle by maintaining the same crack location and by maintaining the same crack depth, then value of damping factor is going to decrease. That we can conclude. This is all about the case number 1. I think that we must make our focus on case number 2. These are the detailed views. These are the conclusions. Means when the location of the crack is kept constant and crack depth increases, then value of natural thickness of the beam decreases. Then all these points I already explained. These are the concluding points. Just say damping factor in the crack beam decreases as crack angle increases. Recently I had explained this point. Means damping factor in the crack beam decreases as crack angle increases. Means for transverse crack it is maximum, for 10-degree crack it is comparatively for transverse crack the value of damping factor is maximum, for 10-degree crack it is comparatively less, and for 20-degree crack it is comparatively less. Means damping factor in the crack beam decreases as crack angle increases. I think that you got. Now case number 2. Free vibration study of V-shape and rectangular shape double-sided cracks in a cantilever beam. Suppose we have one cantilever beam and suppose it is carrying defect, then it is not necessary that the shape of the crack is like this, that I will show you over here. It is not necessary that your beam should carry V kind of crack, because through the literature study I had found that structures, means simply supported beam or cantilever beam or something like that, all these structures are carrying different kinds of crack geometries, like V kind of crack, a rectangular kind of crack, U kind of crack, and all that, and all that. Right now means suppose cantilever beam is carrying crack, and then we will make focus on the shape of the crack. At that time, we will find either V shape from the crack, or U shape from the crack, or rectangular shape from the crack. Right now, then now why I am telling all these things that I will tell you. In earlier days, Ostachovich and Krokzuk, these are two researchers, and they had developed one mathematical, they had converged one mathematical formula for calculating the natural frequency of a crack cantilever beam. Means they had converged this natural frequency formula. Means natural frequency is equal to characteristics roots upon length of the beam whole square under root of Ej upon rho f rho f. Now I will tell you all the things. Bi is what? Characteristics roots of the crack cantilever beam. The omega I, this is natural frequency of the crack cantilever beam. This is Young's modulus value. This is polar moment of inertia. Generally, means we are using I letter for indicating mass moment of inertia, but here I had taken J, and this is rho. Rho is what? Density of the material, and what is F? This is what? Area, cross section of the cantilever beam. Cross section of the cantilever. This means they had developed one mathematical means they had studied one paradigm, and at the end they had converged this mathematical formula, means for the natural frequency. Hello, now I will tell you. Suppose crack cantilever beam is carrying two cracks from one side like this, or suppose cantilever beam is carrying four cracks like this. Two cracks from top side, and two cracks from top side, and two cracks from bottom side. Right now, then, and suppose we have to calculate, or suppose we have to compute the natural frequency of this cantilever beam, then definitely you can make use of this formula. You can make use of this formula right now. And suppose cantilever beam is carrying these kind of cracks, then it is very difficult to calculate the natural frequency. To calculate the natural frequency of this particular beam. And suppose our requirement is that finally we need the value of natural frequency of this particular crack cantilever beam. Then what will be done? And for that particular purpose, what I did, I had extended the mathematical model of these two researchers. For the cantilever beam, means these two researchers had developed the cantilever beam, had developed or converged this natural frequency formula, for this crack beam, and suppose we have one crack cantilever beam, and suppose that cantilever beam is carrying cracks like this, rectangular kind of crack or U kind of crack, rectangular kind of crack. Then we must able to calculate the natural frequency for this case, and due to that, what I did initially, I had solved. Now I will show you. I had solved a number of cases of the earlier researcher. Now I will show you over here. For the kind of crack, they had calculated the value of characteristics root. For the first case, they had calculated the value of characteristics roots is equal to so and so value. Means number of cases they had solved for V kind of cracks. Means they had calculated the value of characteristics roots for number of cases. Then what I did, I had solved 10 cases. I had solved their 10 cases. Means I will explain over here. Means in case number 1, what I did, uh, in case number 1, what I did, I had taken the crack on the cantilever beam over here, and I had considered V kind of cracks only. V kinds of cracks only. Means I had taken the same geometric properties, I had taken the same material properties, and I had taken the same types of cracks, like V kinds of cracks on the cantilever beam, and I had done the simulations using ANSYS software for getting the value of natural frequency. Means when I had solved that particular model analysis for getting the value of natural frequency, means at the end, when I had solved that particular problem, at that time I had got a number of natural frequency. Out of number of natural frequency, I had considered first natural frequency. Then I had taken the value of that natural frequency, and I had substituted that natural frequency formula, natural frequency value in this formula, and I had calculated the value of characteristics node for case number 1. Then for case number 2, once again I had created another model, and I had done the same things, and then I had got the value of characteristics node for the second case. In this way, I had solved. I had keep on solving number of cases, and for 10 cases I had calculated the value of characteristics root for V kind of crack. That I will show you the results over here. Means in the first case they had got this value of characteristics root, and using ANSYS software also I had solved this particular case, and I had almost got the same results. Then for this case also I had solved this case. Means 10 arbitrary, I had taken 10 cases, and I had solved using ANSYS software, and I had got almost same value of characteristics roots for V kind of crack. Then I had decided that whatever approach I am following for getting the value of characteristics root is correct. Then what I did, I had considered the crack cantilever beam which was carrying rectangular kind of crack, and I had done the same thing. Then I had done the same thing, means I had calculated the value of natural frequency, and I had substituted in this formula again, and and I had calculated the value of characteristics root for the cantilever beam which was carrying rectangular kind of crack, and for all the crack specimen, I had calculated the value of characteristics root using their formulas. Means just see, I will show you over here. In his case, for this particular case, means the location of the first crack is 0.1 from the cantilever end. Means L1 by L1, L1 by L is equal to 0.1. Means this is crack location ratio for the first crack, and L2 by L1, this is crack location ratio for the second crack. For the first crack, crack depth ratio was this, and for the second crack it was something. Means this one 0.1. Means in his first case he had got the value of natural frequency is 1.7496. In my case I got this value. In his case he had got this value. In my rectangular crack case I had got this value. And percentage error was 0.665, 0.301. Means and I had solved number of cases. All the cases, means whatever number of cases he had considered, now the same number of cases I had considered. For this case I had got 8.884% error, like this. And here I had got this error. Here I had got this error. Means for most of the cases I had got minimum percentage of error. And through this study I had found that the mathematical model which had developed by these two researchers, can be extended for the cantilever beam which is carrying a rectangular shape cracks. Means this was the findings of this particular crack case. Means whatever mathematical formula they have developed that is applicable for calculating or evaluating the natural frequency of the cantilever beam, which is carrying either V kind of crack or rectangular kind of crack or U kind of crack. And for U kind of crack also, I had published one paper. That case I had not included in this. Means I will show you the conclusion. And means just see, this graph is showing the percentage variation in the characteristics root for V shape and rectangular shape crack case. Just see, means for A2 by H means for rectangular A2 by H means we are taking same crack depth ratio for this kind of crack and this kind of crack, and just see the value of error. Just see the value of error. It is like this error, means very small error. For this and this case, error is comparatively more, but it is less only, means below 11% or something like that. Means for a very less number of cases, I had got error like 9%, 10%, and for a maximum number of cases, I had got less percentage of error. Means just see this particular case, I had got this error. Means suppose the value of crack depth ratio is 0.5, then see the value of error for the characteristics root. It is for uh, this case rectangular shape case and V shape case, error is less. Again, error is less. And here for when for larger crack depth, na, suppose the value of crack depth ratio is larger, then error is more. But in this way, I had extended his mathematical model for rectangular kind of cracks. And all these points I already explained. Suppose we are increasing the crack depth. Now just see characteristics roots, and the B indicates characteristics root, and omega indicates natural frequency. Right now, and in the first case only we had studied when we are increasing the crack depth ratio in the crack cantilever beam. At that time, the value of natural frequency is reducing. Suppose the value of natural frequency is reducing, means value of characteristics root is going to decrease. That I will show. Natural frequency value and characteristics roots value both are directly proportional to each other. That I will show you from the formula. I will show you. Just see this formula. This is natural frequency and this is characteristics root. Bi on numerator is on numerator, and omega I it is also on numerator. Suppose the value of characteristics root in the case number 1, we had studied that when we are increasing the crack depth ratio, then value of natural frequency was decreasing. That we had studied, and in this case also same thing is happening. Instead of natural frequency, we are considering characteristics root for that graph. Just because both are on numerator, means, and because of that, just see the value of characteristics root are decreasing. And similarly, just see over here, just see this particular graph. Suppose we are increasing the crack location ratio. In case number 1, value of natural frequency was increasing, and here the value of characteristics roots are increasing, because that I already told you. And these are the conclusions. What is the conclusion? The theory presented by so and so for a cantilever beam which has 2 open double-sided V-shaped cracks is applicable for the same beam which has 2 open double-sided rectangular shaped cracks. This was the main conclusion of this case study. I think that my presentation is over. Hello. Thanks a lot. Hello.
Yes, sir. Thank you, sir. Thank you for.
it is over, sir.
Okay, sir. Okay. Thank you for your presentation, sir. There are few questions, sir, from participants.
Uh,
Can I ask, sir?
uh,
So the first question is in page number 7 to 8, in case 1,
page 7 to 8.
7 to 8, in page number 7 to 8,
1 minute.
in the question is by using impact hammer.
Yes, yes. This one.
Yes, sir. Yes, sir. Yes, sir.
Uh,
By using impact hammer, about 99 and harmonic, it is showing that 101 to 102. Why it is shifted?
which one, sir? Using impact hammer, na?
Yes.
Means you have to understand the graphs, na, sir? Hello?
Yes,
Hello?
sir. Yes, sir.
Graphs, na? Whatever the page number, tell me.
Participant mentioned it is 7 to 8.
7 to 8, na? This one only?
Yes, sir.
Let them ask. This one, na?
Yes, sir. Yes, sir.
Here the value of natural means error is more, na? Hello? Error is more, na?
Yes, sir.
Hello?
You can continue your answer, sir.
He is asking error is more, na? Means for this particular case. Just see.
Yes, sir. Yes, yes, sir.
The reason is that generally we are providing this is accelerometer, and for this particular case I had located the accelerometer over here. On the next specimens, maybe location of the accelerometer on the cantilever beam would be over here or would be over here, and when we are testing, suppose we are exciting the cantilever beam using the impact hammer, at that time what will happen? Beam will vibrate. Suppose beam is vibrating, then what will happen? Your accelerometer is also going to vibrate along with the beam. Means mass of the accelerometer is going to add into the mass of the effective mass of the beam. Because of that, value of error. Because of that, value of error is more over here. Just see. Hello. From this location to this location, the value of error is more. Means, suppose we are considering the location of the crack nearer to the free end, and at the same time, what will happen? Suppose we have provided crack over here, and suppose your accelerometer is over here. At that time, the effect of accelerometer means the mass of the accelerometer is not coming into picture. But for these locations, suppose we are considering the location over here, then what will happen? Mass of the accelerometer is going to add into the mass of the beam. Because of that error, suppose, hello, all the students, just try to understand. Suppose mass of the accelerometer is adding into the mass of the beam, then what will happen? The value of natural frequency is going to decrease. Hello, because we have one formula, under root of k by m is equal to natural frequency. And suppose the mass of the accelerometer is adding into the mass of the cantilever beam, means value of m we are increasing, and due to that, value of natural frequency is going to decrease, and due to that, we are getting more error at one particular locations, or when we will increase the crack location ratio. Hello.
Yes, sir. Yes, sir. Audible, sir. Audible.
Hello. Ask him whether he understand or not.
Sir, the second question. Can I ask the second question, sir?
Please ask. Hello. Have you got the answer of first question? Hello.
Yes, sir. Yes, sir.
You please tell me from your end. You please reciprocate.
Okay, sir. Okay, sir. So the second question is experimental damping ratio also found by half bandwidth method or by logarithmic decrement method?
That I will tell you. Hello, what I did. Hello. This is experimental. Hello, this is experimental results. Hello, this is experimental result. Means this plot is giving the value of natural frequency, right now, and this plot is giving the relationship between natural excitation frequency and amplitude. Hello, this axis y-axis indicates amplitude, right now. Y-axis indicates amplitude and x-axis indicates excitation frequency. And your question is that how did you calculate the value of
Damping
damping
ratio.
loss factor using half bandwidth method? That is your question, na?
Yes, sir. Yes, sir.
Now I will tell you, using ANSYS software, I had done harmonic analysis. Hello, listen me. Now I will tell you. Now I got your question. I will take some time on that. Using ANSYS software, I had done harmonic analysis. Means I had given sweep of excitation frequency between 0 to 200 hertz, right now. And at that time, my beam, means whatever beam I had considered, it was carrying this value of natural frequency. Means using ANSYS software, I had done harmonic analysis and I had given frequency sweep from 0 to 200 hertz. Means first of all, what I did from the model analysis, I had understood that the value of natural frequency for this particular case is equal to 115 or something like that. Then and from that I had understood that when the value of natural frequency is equal to 115, at that time the value of displacement should be maximum. Then accordingly I had given the sweep of frequency from 0 to 200 hertz. Are you getting this or not?
Yes, sir. Yes, sir.
Because I had to take the decision on the frequency sweep now. Suppose I am considering taking frequency sweep between 200 to 400, but value of natural frequency is equal to 115, means my sweep is not correct. Because of that, I had done model analysis, and from model analysis, I had got the value of natural frequency. It was 150 or something like that, and based on that, I had selected the frequency sweep between 0 to 200. Means what will happen? Now I will tell you, I will give you some information about this. Suppose the value of excitation frequency is equal to 10, then what is the displacement of the free end of the cantilever beam? It was equal to this, it was this value. Suppose the value of excitation frequency is equal to what? Suppose 80, suppose 75, then value of displacement of the free end of the cantilever beam will be like this. Suppose the value of excitation frequency is equal to 100, then value of displacement of the free end of the cantilever beam will be like this. And at one particular time, what will happen? The value of value of excitation frequency equal to natural frequency of the system. Right now, at that time, definitely resonance is going to happen. And because of that, at this particular point, we are getting maximum value of resonant amplitude or displacement of the free end of the cantilever beam. Means I had got this plot using ANSYS software. Then what I did, I had used bandwidth formula that you know, 2 zeta. I will show you that formula. 2 zeta is equal to f2 minus f1 upon fn. That formula, let me see whether I had added or not. That formula is a very well-known formula, right now. Hello.
Yeah,
using
yes, sir,
ANSYS software, I had got this particular graph using harmonic analysis. Then what I did, I have created one horizontal line which is not shown in this diagram. Hello, which is not shown in this diagram. Means suppose the value of displacement is equal to 10 mm. For example, suppose the value of displacement is equal to 10 mm. Then my horizontal line distance from the x-axis will be 7.07 mm. Means it was like this, or not?
Yes, sir.
Or not? Right now, and means horizontal line is intersecting to this particular graph at this point, and at this point, means this point will be f1 point, f1 natural f1 frequency, and this point will be f2 frequency. Right now, means from this I got f2 value, and from this I got the value of f1 frequency, and then I had substituted value of f2, value of natural frequency, and f1 in that formula, and I had calculated the value of damping loss factor using ANSYS software. Means finally I had used the formula of bandwidth method to get the value of damping loss factor. Using ANSYS, I had got this particular graph, and again I had calculated the value of F2 and F1 by using that concept that I already told you, and I had in this way I had got the value of damping loss factor using ANSYS and bandwidth method.
Okay. Okay, sir. Can we do the same in logarithmic method, sir?
Logarithmic decrement, na?
Logarithmic
Sir.
method.
Means, hello, sir. This is
Yes, sir.
experimental plot. Hello, sir. This is experimental plot, and using this particular plot, okay, you can determine the value of damping loss factor. Means that formula, logarithmic decrement, na, means logarithmic decrement is equal to 1 upon xn. Hello, that formula is there, na?
Yes, sir. Yes, sir.
That means I will tell you that formula. Log delta is equal to 1 upon n, means number of cycles we are considering. Suppose number of cycles we are considering as 8, then our ratio will be initial amplitude x0 upon x8, means 1 upon n, natural log of x0 by xn. And suppose we are considering 8 cycles, then n will be getting replaced by a. Suppose we are considering 10 cycles, then n will be getting replaced by 10, and x0 will be means initial amplitude, and xn will be amplitude after 10 cycles. And means for that experimentally we can do that. Means what you have to do, you have to consider, suppose this is initial amplitude, and suppose here cycle number 10 is getting complete. Okay, means we have to measure what is the amplitude at this particular point, and we have to measure what is the value of amplitude, okay, after n cycles, or say for example 10 cycles, right now. Means we have to substitute instead of x0 we have to substitute this value, and instead of xn or x10 we have to substitute this value. Then we will get the value of ratio. You have to take natural log of that, and 1 instead of 1 by n you have to consider 1 because we are considering 10 cycles now. Then you write 1 upon 10, 1 upon 10 natural log of x0 upon xn, and this value we will get from this one experiment.
Okay, sir. Okay, sir. Thank you, sir. Sir, last question. Sir, R value is 0.5 for crack near cantilever end. That means natural frequency drops 50%. What is the corresponding crack depth for this case? I'm repeating the question. R value is
page number show me.
They haven't mentioned. Yes, sir. Yes, sir.
Otherwise you ask.
So I will ask the question, sir. R value is 0.5 for crack
frequency ratio.
Cantilever end. That means natural frequency drops 50%. What is the corresponding crack depth for this case?
And that study I have not done, sir. Your question is very good, but I think that I do not have an answer for this.
Okay, sure. So can I ask one more question, sir? Can cracks of a cantilever beam increases the natural frequencies?
Depth of the crack. So suppose we are increasing the depth of the crack in the cantilever beam at any unique location, then natural frequency will decrease, na?
Okay, sir. Thank you, sir.
It will decrease. Hello. The reason is that suppose we are increasing the crack depth, na, means we are removing more material from the cantilever beam, and because of that, value of stiffness is going to decrease. And suppose value of stiffness is decreasing, value of natural frequency is going to decrease.
Okay, sir. So the final question: shall we take the cracks propagation like X-ray scanner from your analysis? Shall we take the cracks propagation like X-ray scanner from your analysis?
Sir, in that regard, means I cannot say anything, sir.
Oh, okay. Sure. Okay, sir. Thank you, sir. Thank you for your wonderful presentation, sir. There's no more questions from the participants.
My greetings to all of you. I feel honored and privileged in getting this opportunity to propose a vote of thanks on this special occasion. First and foremost, I thank the Almighty for making this event possible. On behalf of FXEZ, I would like to extend my sincere gratitude to the Honorable Speaker, Dr. Vikas R. Kalkar, Gardai Institute of Technology, Ratnagiri, Maharashtra, for accepting our invitation in his busy schedule and delivering such an informative lecture on the topic Investigation of the Effects of Cracks on Vibration Parameters of a Cantilever Beam. I extend my heartfelt thanks to the management, respected General Manager Development, Dr. K. Jayakumar sir, and our beloved Principal, Dr. V. Velmurugan sir, for their moral support and tremendous guidance in conducting such a productive program. Finally, I would like to place on record my sincere gratitude to Dr. Joe Patrick sir, the head of the department, Dr. Zainatul Farida Abdul Ghani ma'am, Dr. I. Nidhimanikam sir, Mr. Sheikh Sulaiman sir, and Mr. Ramkumar sir, and all our colleagues. Without their help and guidance, the program would not have been a grand success. Special mention and thanks to our student, Mr. Jason, for his technical support. This webinar was made successful only because of the well-wishers, followers, and participants of this event. Once again, I thank one and all. Stay home, stay safe.